Thank you very much. Okay. Good evening. I'm very pleased that so many of you are still here. Thank you very much for staying so late. So I'm András Gazdag from Budapest. I'm actually not a local speaker, so I'll just introduce myself very briefly. I'm a PhD student in Hungary at the CRYSYS laboratory. We pronounce it as CRYSYS because it stands for Cryptography and System Security. And I completed my bachelor and master studies partially in Budapest and partially in Karlsruhe Institute of Technology in Germany. And currently, my research field is embedded system security and forensics with two focuses. One is on industrial control systems and the other one is on vehicle security. And this talk is going to be about cars, about vehicle security, and about research I did with a couple of my colleagues in the last year, which turned out to be much more interesting than the way it started. So first, short introduction into the topic. And first I have a quote from Bruce Schneier, the famous cryptographer. Your car is no longer a mechanical device with some computers inside. It's a computer with 4 wheels and an engine. And this is a very important statement because actually it has happened already a couple of years ago. The only thing is that we just didn't realize it. So this is very important and we should change our mindset completely about modern vehicles. And a practical demonstration of this change was performed by Charlie Miller and Chris Wolasak a couple of years ago in 2014. It has become quite famous, their work. I believe most of you are familiar with their works. They basically demonstrated that it is possible to hack a modern vehicle, hack multiple different cars with only cybersecurity as a focus. And they basically hacked into a Ford car, and they were able to achieve multiple different goals, including taking complete control of the car, basically. So a couple of engineering point of view about this. So modern cars are full of embedded controls. We call them ECUs, electric control units. There are a couple of dozens of them in a modern vehicle, and they are interconnected because they realize these modern functionalities with cooperating with each other, and they are connected through multiple different types of networks, and the most used one is probably the CAN network, which is the control area network. And this has worked very well for a number of years, but recently the most new cars have a number of new external interfaces which basically rendered all these vehicles vulnerable to cyber threats, and cyber attacks against these new cars became basically possible. So about this control area network, because this is going to be the focus of this talk. So ECUs are connected together through these networks. A modern car probably have multiple of these networks. This is an example taken from the work of Charlie Miller. This is the layout of this Ford Escape that they are hacked. It basically has two different CAN networks, a medium speed CAN network, this is the high one, and the high speed CAN network on the lower part of this figure. They are there for different purposes. So one is, for example, for all the casualty functionalities, the heating, ventilation, air conditioning, the radio, and everything multimedia related. The other one, the high-speed network, is responsible for all the vital functionalities. So, for example, the ABS, the all-wheel drive functioning, and et cetera, et cetera. And the important thing here is that we have this connector here in the middle called OBD, which is required by law since, I think, 2001 to have in all vehicles manufactured in the European Union. So every car has this connector, and through this connector, it is possible in most cases to access these networks directly. So you can eavesdrop communication through these networks, or you might even be able to inject arbitrary packets through this connection. And this slide is about the CAN protocol itself. So through this network, what is the protocol that the ECUs are realizing? So the CAN protocol was developed in the Robert Bosch company back in the 80s. And at the beginning of the 90s, the 2.0 version came out, and this is basically the same version we are using nowadays. Throughout the years, newer and newer editions of this protocol have been developed. but the basic functionalities are there for 30 years, basically. In 1993, this protocol has been standardized by ISO, and actually already 2 years earlier, so in 1991, the first car was manufactured that already used this CAN protocol, and since then, basically all cars are using this protocol. Down here is a figure about the packets of a CAN protocol itself. There are two options how you can use the CAN network. There is a shorter identifier version and a longer identifier version. In simple cars, so in cars manufactured for people, usually the shorter version is used, and in trucks and in bigger semi-trucks and etc., the longer version is used. The most important thing here is that every CAN packet has an identifier, a couple of flags, a length field, and a data field. And what's in the data field is completely manufacturer dependent, so the protocol itself doesn't say anything about the contents of this data field, and it is usually a proprietary information of the car manufacturer. I have an example about this. So this is a part of a CAN traffic. This is a real. This has been captured in a real car, actually in my car, so in an Opel Astra, and it has been subtracted, so you only see packets with this 110 ID. The CAN protocol itself is designed in a way that the ID of the packets is a priority field as well. So the lower the ID, the higher the priority of a message is. So these packets with this ID 110 are one of the most important packets in the car. And we performed some reverse engineering to understand what's actually contained in the data field of this of these messages. And what we found basically is that here in these couple of bits, the revolution of the engine is encoded. It is not byte aligned. It is mixed together with a lot of different information, so it is not that easy to actually understand the format of this protocol. But with the proper amount of try and error, you get actually the important parts. With a couple of hours of playing around with the car, we were able to find the engine revolution, the speed of the car, the angle of the tires, and the most important and most valuable information that we are looking for in a car. And if you combine together this behavior with the threats that I just mentioned at the beginning of the talk, then you start to realize that we need to come up with some kind of new method to understand this traffic, or at least to capture this traffic for later analysis. Because if there is an attack that I just showed you at the beginning of the lecture, like performed by Charlie Merrill, then you need to have some kind of capability to later analyze what actually happened in the car and try to figure out how you can avoid the same accident again and again. So the first step was that we looked around in other parts of transportation to see what are the options that other transportation mechanisms developed through the years. And probably the most well-known ones are the aviation black boxes. They are very well known, I think. Here are a couple of their properties. So it is a continuous data recording that lasts 1 or 2 hours. So if an accident happens, the previous couple of hours of information are stored in these recorders. And they record a couple of the most important parameters, not everything, but the most important ones. And even the cockpit voice recording is usually stored in case of a big modern jets. Something similar has been developed for cars, for new cars. Actually, it is called the EDR, the Event Data Recorder. It was developed in the United States, and it is mandatory to put some device like this in any new car manufactured since 2015. And the European Union also has a new incentive that starting from next year, a similar system is going to be required to be put in place in every new car. But the properties of EDR is a little different, so it also records information continuously, but with a much shorter time frame. So it is event triggered. This means that the recording is continuous, but it is stored in a shift register, so new information always shifts out previous information. And in case of an accident, the last state of this shift register is going to be stored. So in case of an accident, for example, if the airbag is actually activated, the last couple of seconds of information is stored in this recorder, and you get the most important parameters of the vehicle. So these parameters are kind of subtracted from the CAN traffic, but it's not actually the CAN traffic, but for example, the speed of the vehicle and the angle of the tires and etc., etc. The actual CAN traffic is never recorded in these devices directly. So we analyzed these solutions, and we realized that actually to solve IT accident problems, it's a much different story than to solve traditional accident problems. So the forensics aspect of these two are very different because for a traditional accident, it is a good option to have the last couple of seconds, because that's probably the most important things you need to know to reconstruct the state of the vehicles, to reconstruct the last actions performed by the driver in case of cars. But in case of IT accidents, the story is very different, because the time of the attack and the time of the consequence, the actual accident, for example, could be very far from each other in time. So to solve the problems of IT accidents in vehicles, we actually need to have some kind of continuous collection of CAN traffic, because if we actually find out that there is an accident that might involve a cyber aspect, then it is very important to be able to go back in time as far as possible to analyze what has happened to the car. And if we perform some kind of continuous collection of CAN traffic, then we are going to end up in a situation that we are facing a large amount of data, and we need to store this information somehow, and we need to analyze this information somehow. And this actually led us to the point that we saw that we need to come up with some kind of compression for this traffic that would be a very important part of the complete solution. And we chose to use some kind of semantic compression, because first, it would be much more efficient than just a simple synthetic compression. But the other point is that if we use semantic compression, we might even be able to perform some kinds of calculation on the compressed data, and we don't even need to decompress the data before we can understand some aspects of the state of the vehicle. So next, I'd like to talk about this compression. We analyzed the way CAN works, we analyzed the way ECUs are communicated in a vehicle, and we found a couple of interesting properties that could be used for a base for compression. ECUs are communicating with each other periodically, very, very, very periodically. The regular repetition times are quite accurately predictable, which means that for every packet, we would need to store some kind of timestamp for later analysis, but we don't really need to store a complete timestamp, because based on the previous message, we can predict with a quite high accuracy the arrival time of the next message. And the contents of the messages are often repeating. This is because the frequency of message sending is much higher than the frequency of the parameters change, actually. So we designed the compression that is based on these properties. The first step of this compression is to separate the traffic into different message flows. A message flow is a group of packets with the same ID, basically. So we separate the messages based on their function. Then these flow properties are calculated that I just mentioned before. So for example, the time between two different packets and the arrival time of the first packet, and these informations are calculated then. And based on these two things, we can create a format that is much more compressed than the original traffic log, but still contains the same original information. I can show you an example about this, because it is going to make it much more easier to understand. So this is again a real-life example. This traffic log was captured in my car, and I just simplified it a little bit. So we only have 3 different IDs in this traffic log, but other than that, everything is as you would see in a real car. So what we do is first, we need to separate this message flow into different groups with the same IDs. So this is the first step. Then we can group together packets that has the same data as well. So what we end up is something like this. we have the first group with the ID 260, and with this ID we only see one type of data in all the packets, and then we can list only the arrival times of these packets because that's the only information that is different between these packets. If we do the same for all of these ID types, then we could end up with the description of the traffic, something like this. Then the only thing we need to do is based on these repeating repetition times, we can express these arrival times much more shortly. So this is what we do basically. We first calculate the first arrival time of a message type. Then we calculate this periodicity of the repetition times. Then based on these two information, basically we can describe the arrival times like this. So the first packet always arrives at the 0th timestamp. Then the next packet arrives one cycle later. This is the one before the hash mark. And we cannot completely accurately predict the arrival time of a packet. So we also save a little offset that is basically a correction of the actual arrival time and the predicted arrival time. So we can do this for all different packets, and this is basically going to give us this form of the compressed traffic log. We performed an evaluation of this compression. We created a Raspberry Pi based CAN interpreter, which basically allowed us to get direct network traffic from any car that has a direct access to the OBD port to the CAN network. And we tested this compression algorithm in multiple different vehicles with multiple different scenarios. Altogether, we had multiple hours of CAN traffic logs. And these are the results of our measurement. So we defined two different formats. We have this text-based format and a binary-based format. The text-based format is what I showed you previously. The binary is basically the same information, but represented in a binary format, which is more efficient. And I have these 4 test cases here as a demonstration. So the first column is the original file size, and the second and the 5th column is actually the compressed file size, and there you see the compression ratio. This is just a pure semantic approach of compressing this network traffic log. But then, then we also applied a second step on this traffic log, which is basically a syntactic compression. So if you remember the layout of this compressed traffic log, you can still see a number of zeros after one another, for example, in the data field, and it is worth compress this still in a syntactic manner. So after the first semantic compression step, if we apply a second syntactic compression step, we can achieve even better results, which basically is going to be this. So about 5 or 6% of the original file size is required to store the same amount of information. But the upside of this approach is that we can basically perform a number of operations on this compressed format, because with the semantic representation, we still have an access to the original data, but just in a different way. And then we went on to try to understand the way these attacks worked that were demonstrated by Charlie Miller. And actually we realized that all these attacks can be grouped together in a couple of very simple scenarios. And these simple scenarios are these ones. So it is possible that new messages are inserted into the CAN traffic, and these messages are tried to modify some value that would normally appear in the CAN traffic. And with this modification, the attacker would try to trick the vehicle into a different state. I have a very short example about this that will make it easier to understand. So the attack could modify the network traffic flow in a way that would be very easily understandable and very easily recognizable through this compressed format. And I have an example to show you that. So let's say that the attacker's goal is to modify the value displayed as the revolution of the engine. The original message is something like this that I just showed you. It comes with the ID 110. The periodicity of the message is 10 milliseconds. So every 10 milliseconds, a new message arrives with this ID. And the data looks something like this. Based on our experience now, we know that these couple of bits right at the beginning are representing the revolution of the engine. So that a goal of the attacker could be, for example, something like this. to insert new message into the network traffic log with the same ID, but with a much higher periodicity and with a different data value. This higher periodicity is required because the original source of information cannot be removed from the CAN network traffic. Because that ECU that's actually generating the original messages are still there, and because this channel is a broadcast channel, you cannot block that ECU from sending the original message. So the only way to actually trick the dashboard into displaying a different value is to kind of flood the CAN network with a different value, but with a much higher frequency. So this is basically the goal of the attacker. And if we capture a network traffic log that contains these types of attacks, and we compress that traffic log, this is what we end up with. The first two data are part of the normal behavior of the car. So this is normal data produced by the original ECU. And this third data contains the value produced by the attacker. And as you see, because the network traffic properties were calculated based on the normal traffic of the original traffic, the attack does not align with that one. So we don't get this regular patterns that the amount of cycles passed since the last message is usually 1, and this offset is usually somewhere around 0, small positive or small negative value. What we're going to end up with is something like this. The number of periods since the last message is always going to be 0 because we are sending messages with 10 times the frequency than the normal message. And this offset is going to be much, much bigger because we are actually offsetting inside one cycle of this network traffic. So this is one type of attack. And another type of attack, which I also have an example for, is when an attacker would try to trigger a behavior in the car that's actually produced in the car by the manufacturer, but is kind of hidden. And an example for that is if you know that, for example, Teslas are manufactured in a way that every Tesla has basically the same battery in them, but if you buy a cheaper or if you buy a more expensive one, it's basically a digital limitation of the car to have a shorter or a longer range. And this is an example just for, to show that it is viable to manufacture a car in a way that most of the cars have the same hardware and the limitations of the car are defined in a digital manner. So this could be the goal of an attacker to kind of target hidden functionalities in a car. But to do that, what could actually happen is to achieve this goal, the attacker would need to produce packets on the CAN network that was never previously seen, because this is basically a hidden feature of the car that is usually not used in a normal behavior of the car. So a network traffic that contains an attack would look something like this if we compress a complete new section with a new ID and a completely new data would appear in this compressed format. And it is also very easily recognizable, just as in the previous case. So this was basically my talk. To sum it up, we came up with a compression algorithm for network traffic logs to support the long-term forensics research of accidents. And when we completed this research, we realized that this format is also a very good candidate for intrusion detection. And in the next step of our research, we showed that it is actually possible and it is a good solution for network intrusion detection as well. We have a couple of future work possibilities, and some of these ideas are very promising, so we are working on them. So if you're interested, then stay tuned. We are going to have probably new papers on these topics. Thank you.